Hello students, welcome to Suntech Engineering Solutions. In this topic I will show you a model in MATLAB which is already defined in MATLAB. I will show you this model and its different parameters, its blocks and how it works. So it is obtained from the MATLAB website. If we zoom out the window, you will find the whole model of this system is already obtained from this website, MATLAB website, AC microgrid performance, and the main grid is faulted. So you can download it from here. Just download this model and you will find the same model. I haven't changed anything in this model, so I will find another model, the same type of model, but in which I made some changes. Let's zoom out, zoom in and to show the different blocks. So there are different sections in this model. Like in this way, the first section is the main grid. The first section is the main grid. The different transformers and the breakers are connected to this section. This is the battery section. Inverter is connected and LC filters are connected. The third one is the solid oxide fuel cell. Here in this also inverter is connected. And this one is the asynchronous machine. Three-phase asynchronous machine is a squirrel cage type asynchronous machine. The last one is the PV array. Here also is inverter is also connected to the PV array. So these are generating the DC power, but inverter is converting its single DC voltage to three-phase AC voltage. And all these components are connected to the single transmission line at different locations at different points. This is actually the main section. This is the swing bus. The main grid is connected to the swing bus, and here you will find that there is a three-phase fault injected at the location here after the breaker is injected. So the main grid is actually the 11 kV line, 11 kV grid. It's 50 hertz, producing 50 hertz frequency. And the main grid is initial status is closed, and the switching frequency is important. For each breaker, the switching frequency is different. Most of the breakers have 10 and 10 seconds, and some of these breakers have 100 million seconds, I think. So just you can watch all these values. So the volt is generating at 9.98 seconds, and this is the transformer, step down transformer. It's Y delta connected. Parameters are 25 MVA and 50 hertz, and these are the different measurement find the voltage and current from here. And this is the transmission line. All the transmission lines have the same length. The parameters are different, but the transmission length is same for all the transmission lines connected in this model. So you can find all these ones. So another thing is there are different loads connected, non-critical load and critical load. So non-critical load here, for example, here is active power is 40 kilowatt, and frequency is already 50 hertz, and it's connected on 480 volt. Just look at its frequencies. It's a switching time, and here its active power is 100 kilowatt, and it is connected to nominal phase voltage is 480 volt. Let's look at other parameters. Like another important thing is in this model you will find that we can calculate the different parameters and using the scopes. Here you will find another load. RLC load is connected to the asynchronous machine. The battery is actually 2000 volt and 200 Ah battery, and it is producing power, and the inverter is actually doing the single phase DC, converting it to three phase AC. So these are the three arms ABC connected to main grid. The controller here is very important, but it's actually doing some mathematical logical expressions. It's like here you will find some delays, NOT gates, and comparators, multipliers allow the main grid when to supply power from the battery to the loads. So it's actually doing these things. It is not as important, but we cannot remove it from here because it is already defined in this model. In place of it, we can design our own controller in our own way. So it's the predefined controller. This is the voltage regulator. This is actually a PI controller. Its values are kp and ki values are cons. We can change these values, kp and ki values. This is the PWM generator is generating the PWM signals and giving it to IGBT inverter is actually tuned to 2000 Hz frequency. So the voltage regulator have two inputs. One input is getting from the after the LC filter is getting the Vabc voltages, while the second one is coming from the main grid. And the ABC voltages that are coming after the controller, and controller is getting the input from the main grid. And then the PWM generator is connected to the G of the inverter. So it's you find that there are only three phases of this inverter. So inverting is actually losing some of the power. Another thing, if you download the main model, you will not find this register in your model. This register is the model. If you run the model, you will find there is some error. So you will have to insert a register in series into the capacitor and give it a small value. So this is connected in series to the capacitor. Sim out are important. We are reading these signals. Using the sim out values, we are getting these signals to the workspace. We can save it in different formats, like here it's saved in time series, but we can even save it in other formats. Using these signals, we can detect harmonics in the transmission line or in the circuit in the model. In the workspace, if we click on any of the signal or any of the sim out, we can find its parameter, which parameters are used in this signal. But after running the model, if you run the model, then you will find these values in this workspace. Just look at the data. It's 2500, 250,000 pulses, and it's in three double form. These are actually the three waveforms, three phase waveforms. So these signals are actually the sinusoidal, so we can even get the positive and the negative signals from these out values. SOFC is also connected to the main transmission line using the transmission line and the breakers. The LC filters are used, and the LC filter blocks are used after the inverter. We are using it's an important LC filter or LC filter. So there are actually different types of filters to be used in our models, like the passive filters, the LC, LCL, or LLCL. These are the different types of passive filters we can use. These are actually the simple filters. Active power filters even can be used to inject compensating current and cancel out harmonics. There are different hybrid models by combining the active and passive filters. Shunt filters that can be connected in parallel with the system to absorb the harmonics current. Series filter can be connected in power line or on the transmission line to block harmonics voltages. Notch filters can be used to pass any frequencies or attenuate any of the frequencies. So we can it can be behave like a band stop filters. Active damping filters can be used for in the dynamic systems that can either the control algorithms, the type of control algorithm that can suppress the harmonics resonance. So in harmonics detection, these are the different type of filters that can be implemented in power transmission line. So if you're working on harmonics detection, harmonics mitigation, then you can use these type of filters. These are not very difficult. You can use the same model and implement the different type of filters on and read the signals using the same out values. And in the same out values, actually, can be used to analyze the harmonics using FFT analyzer. In this section, you will find the SOFC block in the yellow color. This is actually the solid oxide fuel cell. So fuel cell is actually a device that can produce electricity just like the battery or the PV array, but it combines the fuel with oxygen from the air and burn it out. It can produce electricity, heat, and water. So in this model, the battery, the SOFC, asynchronous machine or asynchronous generator, PV array, and main grid, these are all the generation sites. So the battery, SOFC, asynchronous machine, PV array, they behave like a microgrid. They are connected to the main grid, at the main transmission lines. Or we can call it a point of common coupling, where the main grid is connected to the microgrids. So all these, the asynchronous machine are actually two types of machine in three phase. This is a square cage, and there is another one round type square cage. So the RLC model is connected to this 20 kilowatt RLC model, and their outputs can be obtained using the scope to observe the waveforms, the voltage and current waveforms. So this actually the PV array also our controller is connected to the PV array. On the irradiance values, the PV array is reading the irradiance values using these two signals. There are two types of signals. lower one is actually the display, and the two signals, these two are the signals that we are obtained that we can get using, we can insert to the PV array, 1000 watt per meter square or 40,000 watt per meter square. So it will change, the first signal will change after the 5 seconds, it will change to 43, almost 43,000 watt per meter square. So it's a variable type of signal, but the lower one is the constant value is getting the 1000 watt per meter square. So in this case, we are actually using the first signal. It's getting 40,140 watt per meter square. It's getting the irradiance value. In Simulink model, there is one another PV array model block to which we can connect the irradiance as well as the temperature. So these two can be used as inputs. But here we can only connect the irradiance to the PV array. If we click on the PV array, we will find its parameters. Here it's actually the model type is 305 watt. It's a number of cells connected, 96, 30 cells are connected in series and 56 in parallel connected. So it's a series parallel connection of PV modules. Here the LC filter is used just like a battery. Here there is a voltage regulator section. Here is the same controller, same type of controller that we can compare the signals and getting the output signals in three phase to the inverter output with the inverter output. Here it's a three-phase ground transformer connected to the ground. It's behave like just like we can use it in three-phase ports, but we are not using three-phase ports. So we are using this model in learning harmonics detection. So this model can be used in harmonic detection. We can actually make some minor changes in this model, and we will find these in another model. We'll find it in another model. The sim out values is actually, if you can find the sample time, we can change the sample time as well. It's saved in time series. So if we need harmonic detection, then we can save it as in another format. The PWM regulator has if you can find it, its sample time is fixed in TS. It's a time delay, its sample time is also TS. It's already defined in this model. Here the CI shows the current transformer while the VDC shows the voltage. So using this block VDC, we can read the voltage at these terminals plus minus the voltage generated, the potential at these value at these points plus minus of the battery, and using the CI we can read the current pulses. So we are using these two values to multiply it using a multiplier. You can see this signal is going to the multiplier, and the voltage signal is also going to another multiplier into the same multiplier. These two are voltage and current are multiplying the DC voltage and current, and we can get the output on this scope at the third waveform on the same scope. So this one is actually the power 2 is it's reading the voltage signal and the current signals. This is in three phase. So these three phase signals are voltage and current waveforms. Its output is PQ, means the real and reactive power. We will get the real and reactive power of these signals. The voltage is coming from the output of the LC filter and the current of the output filter, and we can run these using the scope. We can obtain the pulses using the scope. So the three-phase transformer, the other parameters, we are not changing the other parameters. There's a three-phase environment, we can use it in PU or signal. You can observe it whether it's in PU or not per unit. It's a base value or nominal voltage is given. So its nominal voltage of this whole model is 480 volt. It's actually that this transformer is converting 11 kV to 480 volt. So this is the only transformer in this model. These are the waveforms that we obtained from this, showing the voltage of the battery, 2000 volt, 2000 is the current of the battery, and these are the output of the inverter. And the last one is, I think, just go through this one and check its signal. The voltage waveforms. The second one is the current waveform, and the third one is the voltage waveform after output of the inverter. and this one is the current output current of the inverter, and the last one is the output voltage of the inverter of the filter. After the filter, we can use we get these waveforms, the last one. So if you zoom in this window, these waveforms, you'll find that the last one you can see sinusoidal, and this is the current waveform. The voltage is waveform. It's the output of inverter. You can see it's a square waveform. Square form. Yeah, this one. The third one is the square waveform. The fourth one is the sinusoidal, but it's have some harmonic. But the last one is smooth using the LC filter. So using the LC filter, we can improve the waveforms and we can reduce the harmonics. These signals are actually, I think, these are the output M modulation index value. The first one is the modulation index. The second is the real and reactive power, and the third one is the voltage and current or multiplier. So this is the power, actually showing the DC power, and the fourth one is I think it's the grid voltage, and the last one, yeah, it's actually the comparison between the two signal between the two phases. The PV phase is the comparison of the two phases, and the last one is I think this is also the comparison between the two phases. The two phases, yeah, okay. Let's connect the first phase, phase A, and the first phase after before the break, before the transmission line, and after the transmission line, connected on the main grid. So you can see here the comparison is reduced and almost becomes zero. These are the difference actually. The signal, the phase is difference. It's actually improving and it's going to zero. We can use it using feedback pulses. We are using feedback pulses from the main grid, comparing the battery and the grid voltages, and we can compare and we can find that where is its difference. So in the starting, it's the difference. Just move to the LC filter where the L inductor value is changeable. These parameters, inductor value can be changed, and capacitor value can be changed. Here we can use another L to use it as LCL filter. So I have made changes in this model to make it test it using LC and LCL filters. So these are three filters used in this model. One is with the battery, second one is the SOFC, and third one is used after the solar PV array. So, but in another model, I've used these filters as well at the load sites. So I have used actually the pulses at the output load sites. You can see at every load we are using LC filters or LCL filters. This is the same model that I have redesigned. You can see in these variables actually saved in structure with time. In the last model we have used it with time series, but this one format is saved with structure with time. So this is important. We can actually use it as a harmonics detection. So for harmonics, you have to use it and save it in structure with time. Just go to the discrete power view. I just click on this, and you will find how to analyze the THD analyzer using FFT analyzer. Just click on the FFT analyzer, and in a few seconds you will find there is a window on FFT analyzer. This is the same window that we obtained. So these are the structure with time. You can see here in the structure with time, these are all the signals that we are obtaining from this model. The structure same out 1 up to same out 16. So we can use it for harmonics detection. We can change these values. Fundamental frequency in our model is 50 Hz and frequency is 20 and 2000 Hz. So we can change these two values and just click on the compute FFT. You will find the FFT analyzer, FFT, THD harmonics. You can update it and then compute FFT. Here you can find the THD is 14.23%. Sure, it's not actually it's a very high THD. These amount values are all connected on the current values. It's not adjusted for the voltage. So we are only using the current waveforms. You can even change the number of cycles, and you can even make changes in the start time. You can see the THD is also increased 50.4. So there are different parameters. You can check it. This is the same window that we are getting the 5 signals, the number of cycles starting from the 0 up to 5 seconds, and you can compute in this way. So you can even change the dimensions. and the number of cycles. FFT window, we can change it to FFT window or signal. In this is the same model that we have used it to study the harmonics. There was a fault analyzed, fault injected in this voltage, but we have removed this one. Voltage and current waveforms can be read using this scopes. This is the voltage and the current waveforms. The three-phase grid output voltage and three-phase single-phase battery output voltage, SOFC output voltage, three-phase asynchronous machine, and this is the PV output voltage waveform. You can see here there are some changes in these signals. The current waveform is going to 0. It's not providing current to the load. So it goes off the controller. I told you that before that the controller is doing all these things. I have run it for 0.5 seconds, so it's not. It should be more than 10 seconds or 20 seconds for steady analysis. But it was heavy, so I just tested for 0.5 seconds just to show you the output in a small time frame. The breakers are connected at different locations. We can change the timing of these. We can adjust the timing of these breakers. We can even change the transmission lines, parameters, their length, etc. We can change multiple things in this model. So this is actually a very important topic. You can use this same model for different analysis. If you are facing any issue in this model, you can ask me or in your comment box. Email, write in your email if you have any academic project in your hand and you are facing some issues, you want my help, then I'm always available. So don't be hesitant and ask me anything that you want. So Simulink models are very heavy. This model can only be run in 2024, I think 2025 model, MATLAB. If you have older versions of MATLAB, then this model will not be run in your MATLAB. So try to use the latest model. If you haven't paid version, then you can get the trial version. These are the different waveforms that I have done using the LC filter and LC filter. So this is you can see the critical load outs here, waveforms. I don't want to explain it in detail, but I just want to show you. These are the output of the THD values for the different signals. Just change the SIM-out1 or SIM-out2 and update the signals and run it. You will find the THD of that signal. So these signals I have used it before inverter and after inverter in my model. In some places I have used it. I have used it after inverter. Before LC filter, I have used one signal and one signal after. So these are the output waveforms of LC and LCR filters. I have designed the LC filter and LC filter using these equations. These are simple mathematical equations. Just put these and use it in your calculations. The resonance angular frequency, and you can use the C, how to find the C value, how to find the L value using these equations. The LC filter and LCR filter has their own equation. So LC filter has 1 divided by pi square root LC. You can use this, and that's not one. So actually you can use these filters to compare the analysis using the different values. You can give this table, the comparative and the comparison of this table, the THD values. You can find that the older versions behave better than the new version, because I have used actually the tuned value. I tuned these values, but not in accurate form. This actually this model is under process, and we will make many more changes to it and improve the output waveforms. The Total Harmonics Distortion, we will try to improve it and use the active damping filter also along the LCR filter to improve its output. So in LC and LCR filter, the LC filter will behave better, but LCR should behave better than the LC filter. But in our case, it's not the same. So here, in place of controller, we can use the active damping filter. This is the mathematical expressions in algorithm form, so we can use it in place of this controller, and the results will be better. So the same model can be used as a fault analysis, and the damping we can use this. This is a very complicated, extended, but an important model. You can use it in your different type of analysis. And please don't forget to like, comment, and subscribe my channel to use such type of topics. And ask me anything in the comment box if you face any type of difficulties. Thank you so much for watching my video.